All right, in this video, we're going to be talking about section 3.5, which is going to be using and learning about exponential and logarithmic models. So today, we will start with a couple of warm-ups. So these might be a little bit challenging, but let's see what you can do with them. Go ahead and pause the video and give them a try. All right, in order to solve this problem, I do not like this denominator there. It seems to be complicating matters. So we should multiply both sides of the equation by the denominator. And by doing so, we should land at 525 equals 275 times 1 plus e to the negative x. Got a couple of options here. I could distribute, but I think it would just be easier to divide by 275. I'm going to go ahead and just fully use my calculator on this one. So dividing by 275 is going to leave me with 1 plus e to the negative x. And then I could reduce it, but I'm heading for a calculator anyway, so let's just do it. 525 divided by 275 is a pretty ugly number, 1.909 repeating. So I'm going to write it down as 1.909, but I'm going to make sure that I leave it in my calculator and use that number as I continue to do the work. So now I'm going to subtract 1 to get the e by itself, which of course is going to give me 0.909 repeating equals e to the negative x. And then I am going to take the natural log of both sides to cancel out my e. So that's going to give me the natural log of 0.909 equals negative x. I'm going to divide or multiply by negative 1, and x is going to equal negative natural log of 0.909. All right, so let me subtract the 1 on my calculator to get the 0.909 repeating. And now I'll take the natural log of that and change the sign. And I get x is approximately equal to 0.0953. So we'll leave it at 0.095. Okay, there we go. And let's take a look at part B over here. Part B, I've got to get rid of the 8, 8 to the power. So to cancel out the 8, I need to take a logarithm. So I have two choices. Actually, I have more than two. One choice would be to use log base 8, and that'll make it look pretty, but won't necessarily make it easier to find my answer. So I'm going to demonstrate this again. We kind of did this when we talked about the change of base formula on the previous lesson. But let's go ahead and look at it going both directions again. So this problem I'm going to take log base 8 of 8 to the 0.4x, and I'm going to take log base 8 of 5. Log base 8 of 8 is 1, and so again, visualizing that the 0.4x comes down, then you have 0.4x times 1. So I am left with 0.4x equals log base 8 of 5, and then x equals dividing by 0.4. I don't like dividing by 0.4, and I certainly don't like 1 over 0.4. So let's think about what 0.4 really is, which is 2/5. So I'm about to divide by 2/5, which would be the same as multiplying by the reciprocal, which would be 5/2. All right, so there's my answer. But if I want to go to calculator or decimal to get a better answer here, then I need to use my change of base formula. And that would either be natural log or log. I'll go ahead and do log. So log of 5 divided by log of 8. So then Mr. Calculator, and I get, let's see, log of 5, enter, divided by log of 8, enter, multiply by 2.5. And I get approximately 1.935. Alternatively, I could have just from the beginning taken log base 10 or log of both sides instead of log base 8, which would have given me log of 8 to the 0.4x equals log of 5. The 0.4x comes down, and then divide by log of 8. And once again, divide by 0.4, which is 2/5. So I get x equals 5/2 log of 5 over log of 8, which is exactly what we have right here. So ultimately, it does not matter if you choose to do it one way or the other. It is your choice. And hopefully that makes sense. All right. So today we're going to talk, I guess, really about story problems. We're going to talk about uses of logarithms. So we're going to really just focus on kind of 3 common logarithmic models and exponential models. And mostly we're going to be working with the growth and decay. So exponential growth and exponential decay are technically, we use the continuous, we use the natural base e, because when we're working with models, very rarely are what we're going to be kind of modeling things that are discrete. Like 1 second goes by or a minute goes by, and then the thing doubles or the thing triples or the thing gets cut in half. Usually, what's happening in a situation with growth is that all along things are changing as we go. So it's more of a continuously changing and updating system. And so that is why we will be using E as the base of all of these problems. All right, so exponential growth, if you look at this, this is just our common exponential equation. A is a vertical scale change. Also, it's sort of the initial amount. And the reason we call it the initial amount, because as at x equals 0, then b times 0 is 0, e to the 0 is 1, and we get a. So at x is 0, we get a. So that is your y-intercept, essentially, is your a value. It's also the vertical scale change because your typical y-intercept of 1 turns into a. So it's a times as tall. All right, and then the b is the it's a horizontal scale change, but in this case, it's really the rate. And we'll kind of play with this as we go. So if b is greater than 0, so b is a positive number, then that's going to be growth because our e is 2.718, and so it's going to be growing as it's raised to a number bigger than 0. If b is, and then if b is negative, right? So it says b is greater than 0, but now it says negative b. So that would make this now a negative term. Then that makes it 1 over e, and that means we're going to get smaller as we go. So we already know all of this. Exponential growth model is going to look like this, and an exponential decay model is going to look more like this. The closer the b value is to 1, then that means we're growing very slowly, because if we're at 1, if b was 1, then the graph would not grow at all. It would be a horizontal line. So as b creeps a little bit bigger than 1, then that's going to start to curve the graph up over time. The bigger the value, the faster it's going to curve. Okay? And so we've got that. And then, of course, we've got our logarithmic models. And logarithmic models are in this form of a plus b natural log or log of x. And we know that those, of course, are in the form of a logarithmic graph. Okay, so let's go ahead and jump in. Example number 1. we're going to find an exponential growth model, or it could be decay, I suppose, that is in the form of what we just talked about, y equals a e to the bx power, whose graph passes through these 2 points. And so, in order to answer this question, we have an x and a y value, and we have an x and a y value. And so we can plug those in, and then the only variables we'll have left is a and b. But we have 2 sets of points, so once we plug them both in, we ought to be able to use a system of equations to solve. All right, so let's go ahead and see what happens. I'm going to, for reasons I'll explain in a minute, I'm going to start with the 3 and 1/4. So y is 1/4. Let's go to black here. So if I'm going to use this model, I've got 1/4 equals, I don't know what a is. E is E. I don't know what B is, but X is 3. So I've got 1/4 equals A e to the 3B power. So once again, you'll notice that we have now a single equation that has 2 variables. Don't get confused. E is not a variable. E is 2.718. So I don't know A and I don't know B. So then I go to my other point and I substitute that in as well. So I get 1/2 equals, I don't know A, e to the bx power. So in this case, it would be 0 times x, 0 times b, excuse me. Okay, so if that was any number other than 0, then now we'd be sitting with 2 equations with a's and b's, and then we would need to do a substitution. But if we think about what we just talked about a minute ago, 0, 1/2, well, that is my y-intercept. And A is my y-intercept. So if I had noticed that, I could have just jumped right ahead and said that, oh, I know that A is 1/2. But we need to be prepared to answer a question where they don't give us 0 as the point. And again, in that case, you would just be sitting with 2 equations. And then you would want to do a substitution. But if I simplify this out, 0 times b is 0, e to the 0 is 1, and this, of course, just tells me that A is 1/2. So I don't have to really do any fancy substitutions other than really I can plug in my A value now. So I have 1/4 equals 1/2 e to the 3b power. So now I need to solve for b. So I'm going to multiply by 2, giving me 2/4 or 1/2 equals e to the 3b power. I'm now going to have to take the natural log. I'm going to go ahead and do this up here. So I get the natural log of 1/2 equals the natural log of e to the 3b. Natural log of e is 1, and so once I bring again the 3b down, I'm left with simply natural log of 1/2 equals 3b. Or b equals 1/3 of the natural log of 1/2. So if I was going to leave my answer in terms of an exact answer, then I would have this kind of ugly looking equation. So let's go ahead and write the equation. It would be y equals a, which is 1/2, e to the b power. Well, b is now 1/3 natural log of 1/2 to the x power times x. That's pretty ugly. So that's technically correct. It's just kind of ugly. So let's now get an approximate model by turning that all into a decimal. So I get natural log of 1/2 and multiply or divide that by 3. And I get 1/2 e to the negative 0.231 x power, which seems to be telling me that we have a decay situation. And we can kind of take a look at this real quick. Let's kind of see if we can sketch out this graph by the points. So let's call that 1. So we have 0, a half. And then I'm at 3. And I'm at a fourth. So this is going to be a very slow decay. Anyway, that would be our model right here. All right. Let's move on. Let's take a look at a common familiar problem. So we looked at this back in the day, and we answered this as a half-life. We used half, right? Because half of the cookies are gone. So I just use this as a sort of silly way of illustrating half-life. And so when we're doing half-life, we know after, in this case, 1 hour, half the cookies are gone. So we didn't use an E model. We used simply 1/2 as our base. So just to remind you, I think our equation would have looked something like this. My cookies after a certain time were going to be 32, and then we used 1/2. And then we used a model like if we're plugging in hours, right, then in 1 hour, it would be 1 half-life period. So as long as what we're plugging in is in hours, then we would just be to the t power. 1 hour multiplying by a half. 2 hours multiplying by half again. All right. And this is an okay model, but if we consider the fact that most of the time when we're doing these half-life problems, the cookies, if you will, or the radioactive isotopes, are constantly being reduced. They're constantly decaying. And so a model with an exponential, with E, a continuous model, makes more sense. So let's attack this using this different model, using our exponential decay model from above. So the same one as before. All right. So our A value, I've just written as C sub 0 this time, because that would be the cookies at time 0, which is, of course, our y-intercept. So just like we talked about above. So in this case, we could plug in the point at time 0, we have 32 cookies, but that's simply going to lead us to a place where the initial cookies are 32. So I know that we really have C of t equals 32 e to the kt power. And you'll notice we have no other information other than the half-life period. So let's do this. We don't know what's happening after 10. Like there's no second point like there was in the previous question. But there kind of is if we make up our own. Because I also know that at time 1 we have 16 cookies. So let's use that as our second point. So I'm going to plug in that I have 16 cookies at time 1. So I plug in 1 for t and I get k. So I get 16 over 32 is a half equals e to the k power. I'm going to take the natural log of both sides, which is going to give me k equals the natural log of 1/2. Okay, so if we go ahead and find that on our calculator, we've got the natural log of 0.5. So k is approximately equal to negative 0.693. And so then our model with an exponential is C of t equals 32 e to the negative 0.693 t power. And I'm going to change my equal sign to an approximate equal sign. All right. So that is a continuous model for the number of cookies left at time t. So now if I plug in time 1 or time 2, it'll work just fine, but it also works just fine if t is a decimal. All right, so I can plug in not just at the hour and the 2 hour, I can plug in anytime I want, and it'll deliver the same answer as the above. So this is just kind of a formality because honestly, these two give the same answers, but oftentimes it's this k value that we're looking for because that k value is our rate, right? So thinking about our exponential PE to the RT power, that's all we're doing right here. So this negative 0.693, that is my rate. So that's like saying we have a 69% decrease as time goes by. All right, not sure I'm explaining this very well. It's easier to do in person. I want to point out something, and maybe actually I'll wait to point it out in the next one, and that's what I'll do. So let's use our model now to figure out how many cookies we have after 5 hours. So I'm going to find C of 5 equals 32 e to the negative 0.693 times 5. Now remember, this is an approximate model because we rounded, and the less we round, the more decimal places we include, the more accurate our answer would be. So at 3 decimal places, we'll be close. Okay, let's see here. I'm going to do e to the negative 0.693 times 5, all in the power. And then I'm going to multiply that by 32. And I get C of 5. And with proper rounding, so technically my answer is this 1.0007. But I think we can see that with a little more decimal places, had I gone out more, it would have been even closer to 1. So I think we can go ahead and say that the answer is 1 cookie. And that is exactly the answer we would expect because in 5 hours, using our previous model, that would just mean we're cutting it in half 5 times. So half of 32 is 16. That's 1. Half of 16 is 8. That's 2. Half of 8 is 4. That's 3. Half of is 2. And then our fifth one is 1. 1 cookie. Okay. Let's take a look at this again now with a more realistic problem. All right, so suppose you have a particular radioactive substance that has a half-life of 25 years, and the initial sample contains 80 grams. Find a function in the form of m of t equals m sub 0, meaning the initial mass, e to the kt power. All right, so once again, I know what the initial mass is. They gave it to me in this case, is 80 grams. So I've got m of t equals 80 e to the kt power. So I'm on my way. I just don't know what k is. So now let's solve for k. So once again, I need another point. I have the point 0, 25, and that's what got me my initial value. But now I also have the point that in 25 years, we're going to have only half. So that would be 40. So I have 40 equals 80 e to the 25k power. I divide by 80, and of course I'm going to get a half because that's how we set it up to work. I'm going to take the natural log of both sides. Oops. 25e. I'm sorry, natural log of e to the 25t. The 25t comes down. Natural log of e is 1. So we're left with 25t equals natural log of a half. So time equals 1/25th natural log to the 1/2. Or t is approximately equal to, let's see here, the natural log of 0.5 and divide that by 25. So I get negative 0.027725. I'll go to 7, I guess 8. All right. So then the model in question would be m of t equals 80 e to the negative 0.2028 t power. And part B, use your model to determine how long it's going to take to get to 10 grams. So this time, I'm not plugging in a time. I'm going to try to solve for a time. So I'm going to just simply find out, when does m of t equal 10? So that would be 10 is equal to 80 e negative 0.028 t divide by 80, and I get 1/8. 0.028 t. Time for natural log. So I'm going to take the natural log of 1/8. I'm going to take the natural log of e to the negative 0.028 t, which is going to give me natural log of 1/8 equals, that comes down, natural log of e is 1, negative 0.28 t. I'm going to divide by that, and so I get the natural log of 1/8 divided by 0.28 is going to be my time. So my time is approximately equal to natural log of 1/8, and then that's a negative, divided by negative 0.028. Looks like I lost a decimal in there. My apologies. There's a 0. And there's a 0 here. And so I got time is approximately 74.266. And this would be in years. Okay. There we go. And let's do one more. Example number 4. Same setup. 570 years for a half-life this time. Find a model of this form for the amount remaining after t years. Now, I want you to notice we have a little issue here. They have not given us an initial amount. All I know is 570. But let's think about this for a minute. Because if I did know the initial amount, in fact, let's just say that we do know the initial amount. Let's say the initial amount is at the point 0 and m sub 0. Then how much do we have left after 570 years? That would be one half-life period. So whatever m sub 0 is, I now should have half of it. So if I plug that in, I get my, number one, plugging in m sub 0, I get my equation. And so I'm going to now plug in, so let's go ahead and write this down, m of t. So I plug in my initial amount, there it is, e to the kt power. Now I'm going to plug in the second point I know, which is I have half of my initial amount after 570 years. So my next step is to divide by m sub 0. And sure enough, as they cancel out, I get a half, which is what I would expect to get because that is always going to be the ratio of what I have left if I've put my second point in as the half-life period. Okay, you'll notice it didn't matter what my starting amount was when I go back and look at the previous questions. Previous questions, I started with 80, and then I knew that half of that was 40, so I just plugged that in, and when I divided, I got the half. On the one before that, with the cookies, the same thing happened. I knew that after 1 hour, we had half of the cookies, and so when I divided, I got a half. So that is always going to happen when you're doing half-life. So now that I have this, I can solve. I get the natural log of a half equals the natural log of e to the 570k, or 570k equals the natural log of a half. So k equals 1 over 570 natural log of a half. Or k is approximately equal to the natural log of 0.5 divided by 570. Negative 0.0012. I'm going to go out to 4 decimal place on this one. Okay. So now I know my model kind of is m of t equals whatever my initial amount is, which I still don't know, e to the negative 0.0012 t power. All right, now it says if the initial amount was 32, so now they just go ahead and give it to me, the little jerks, then how much am I going to have after 200 years? And let's think about how much we're probably going to have. So the half-life period is 570, and we're only going 200. So if we started with 32, after 570, we'd be at 16. So we're going to have, quite a bit more than half. We're going to probably lose about a fourth or so, but let's find out the exact amount. So let's plug in 200. And we get e to the negative 0.0012 times 200. Looks like I'm going to have 78% still left because I'm now, if you look at the math here, I'm at 0.7866 and some change. And so since I'm rounding, we're going to say approximately equal to. So that's going to be approximately, like I said, about 78, 79% of 32. So multiply by 32. And it looks like I have about 25.17 milligrams remaining. Okay, I hope that makes some sense. And if you have questions, let's talk about it in class.